Okay, guys. Good morning. Welcome back. This is, of course, Calc 1, section OH1. Today we are going to learn from Kevin all about mins and maxes. So I will come over here and do our normal little intro, and then I'm going to hand it over to Kevin.
Last night I sent you an email with the links to the YouTube videos.
I saw that come in. I haven't looked at it yet, but if you would like, I can stream them from my end. That way we have kind of a single source here. Is that
Yeah,
what
sure, that sounds good.
All right. Alrighty, so here we are, and today, so was there a fourth student teaching? Kevin. Lecture on 4.1, which is mins and maxes. And I got a chance to look at what I think is probably a slightly earlier version of Kevin's material a few days ago. So we're in for a nice treat. Kevin has definitely put a lot of time into this, and I think you guys will enjoy it very much. So I'm going to turn off my share just in case there's any private emails in there that people don't want other folks seeing. And then I'll turn it back on once I've pulled up Kevin's videos here. It's been a busy weekend. All right. Okay, so I'm going to open this one, and I'll go ahead and queue up the others. All right. All righty, let's come back here, turn this on, and give our full attention to Kevin's presentation here.
All right, so today I'm going to be teaching us about chapter 4.1, minimum and maximum values. So the absolute or global maximum is the highest coordinate value reached on a graph. And the absolute or global minimum is the lowest coordinate value reached on a graph. So what we can gather from this graph right here from the textbook is at this point 3, 5, right at the top, right here is the absolute maximum. And this point right here at the bottom is the absolute minimum. And another thing we can gather from this graph is that the limits of f on the graph, or the highest and lowest values of f, in this case, 5 and 2, right at here at this point, 6, 2, those are called the extreme values. So here we have the local maximum and local minimum. Local maximum is defined as the highest coordinate value of f if f of c is greater than f of x, as x is on the curve near c. So in other words, if you look at these hills right here, if you're looking at the top of one of these hills, it's not necessarily the highest point, like f of b right here. It's not necessarily the highest point, but it is the highest point on this curve. So that would make it a local maximum. Same thing with the local minimum right here. At f of c, we have a point that is the lowest point in between these two curves, but it's not the lowest point on the graph. We can also see that the graph has an absolute minimum and an absolute maximum. Here we have an absolute maximum at f of d, the highest point on the graph, and we have an absolute minimum here at f of a, the lowest point on the graph. So for the maximum and minimum behavior of cosine, as we can see here, we have cosine, which is bound by 1 and -1 in its oscillations. So when we look at a graph of cosine, we can see that 1 and -1 constitute the local and absolute maximum and the local and absolute minimum respectively, and they can be the same thing. So always remember, whenever you're looking at a graph, you can have a value be both the local and absolute maximum and both the local and absolute minimum. So we have here a quick example. Identify the local and absolute maximums and minimums. So when we look at this graph, we can see here, you can get that the highest point right here, -1, 37, is the absolute maximum. 37 is the highest y value of this coordinate, so it's the absolute maximum. we have a dip in the curve right here. It's not the lowest point, so it's a local minimum right here at 0, 0. Here we have a hill, local maximum at 1,5. It's not the highest point, so it's just a local maximum. Here we have an absolute and local minimum here at the bottom of this hill, 3, -27, which as you can see, it is the lowest point on this graph.
I want to, it's good that there's a break here because I want to take a second to discuss something that is, that the book actually gets a little bit wrong. So Kevin's definition, we say f of x has a local min at x equals c if f of c is like the smallest value anywhere nearby. So f of x is greater than f of c for all x near c. And the other definition for local max, f of x has a local max at x equals c if f of x is less than or equal to f of c for all x near c. Kevin didn't do anything wrong. His work there is perfect. And this is how the book defines a local min and a local max. But sometimes you'll notice in WeatherSign, it can be a little bit picky about things that are both local and absolute maxes. So I just want to kind of redraw a similar sort of example here for you. Okay. I'll call this first x value here A. I'll call this x value here B. Call this x value here C. Call this x value here D. Call this one up here E. And I'll call this last one over here F. There are local extrema at all of these. A, B, C, D, E, and F. So this is a local max. This is a local min. This is a local max. This is a local min. This is a local max. And this is a local min. The absolute extrema, so there's a local max or min at every single one of those points. This is the absolute min. And this up here is the absolute max. But every one of those points is also a local min or a local max. So your absolute extrema are always also local. Whether they occur at the endpoints or somewhere in between doesn't matter. Your absolute extrema are also always local extrema because of course they satisfy these definitions, right? If f of c is the smallest y value on the graph anywhere, then of course it's the smallest y value nearby. So I just wanted to inject that. The book gets this a little bit wrong. The book doesn't really get it wrong, but the WeatherSign interpretation of the book gets it a little bit wrong. So sometimes when you find an absolute max or an absolute min, if it comes from an endpoint, the book will tell you that that's not a local max or not a local min. But the truth is, it's both. So I just wanted to inject that really quickly. We're going to go on here to his second part now. Any questions on what I'm saying there? Like, in other words, let me draw an even simpler example here. This is both a local and absolute max. And this is both a local and absolute min. WebAssign would tell you that here at A, you have an absolute min, but that it's not local. And that over here at B, you have an absolute max, but it's not local. But the truth is it's both. The truth is it is both. Because if you look nearby, this is the smallest y value on the graph anywhere near A, right? If you just focus on this little window, this point right here is the lowest point. So of course it satisfies the definition of a local min. And similarly, this point clearly satisfies the definition of an absolute max because it's the tallest point on the graph anywhere, but it also satisfies the definition of a local max because of course it's the tallest point nearby, it's the tallest point anywhere. All right, let's come back here.
Here we have the extreme value theorem, which, as we learned before, if f is on a closed interval a comma b and attains its absolute maximum and minimum.
I'm sorry, did I skip over something? Is this? Yeah, this is the correct second part, right? Part one, part two, okay.
Values at f comma c and f comma d on that interval, then the values of f at c and d are called extreme values. So what it's basically saying here is talking about the y values or the highest values of f reached at the absolute minimums and maximums. Here we have Fermat's.
Sorry, and before we bump onto that, I remember talking with Kevin about this. There's one thing that I want to inject here too. The purpose of that extreme value theorem is to guarantee the existence of something. So I'm going to give a slight rephrasing of it. And I'd like you guys to write this down. Any continuous function on a closed bounded interval must attain an absolute min and an absolute max. Kind of the idea being if your function is continuous and the domain that you're looking at is a closed bounded interval, then no matter how hard you try and avoid it, there will be a tallest point on the graph and there will be a lowest point on the graph. So in this picture, for example, my absolute max is at x equals b. And my absolute min is right here. I'll call this C. And kind of the purpose of this theorem is the must, right? If your function is continuous and you're looking on a closed bounded interval, then there's no way to avoid having an absolute min and an absolute max. You must have both of those things. If your function is not continuous, or the interval you're looking on is not closed or is not bounded, then this falls apart. So this gives a necessary criterion, or I should say a sufficient criterion, to guarantee the existence of an absolute min and an absolute max. So if I give you any continuous function on a closed bounded interval and say, find the absolute max, find the absolute min, you know that I'm not fucking with you. You know that one exists and you have to be able to find it. What Kevin's about to go on to explain is how to find it. And Fermat's theorem is a big part of that. So I'll rewind just a couple seconds.
So what it's basically saying here is talking about the y values or the highest values of f reached at the absolute minimums and maximums. Here we have Fermat's theorem, which says if f has a local maximum or minimum at a number c, and the derivative of f of c exists, then the derivative of f of c equals 0. So basically, for example, If a function has a local maximum at 3, 5, like we saw in the first example, then f of 3 equals 5, then the derivative of f of 3 will equal 0 if it exists. Now, note, just because the derivative of f of z equals 0 does not mean there is a maximum or minimum. In other words, the converse of Fermat's theorem is generally false. And here we have a proof of Fermat's theorem. So suppose that f has a local maximum at c. That's a given. So step 1, first thing we do is we take f of c is greater than or equal to f of c plus h, and we subtract f of c from both sides. So here we essentially set it equal to 0, and the inequality is reversed here. So we have f of c plus h minus f of c is less than or equal to 0. Then we divide both sides by a positive number, h. And the fact that it's a positive number is really important at this point in the proof, because the sign of h, or whether h is greater than or less than 0, is going to affect how we prove the second part of this theorem. So we divide by h, like they said, so we get f of c plus h minus f of c over h is less than or equal to 0. Then we take the limit as h approaches 0 of both sides. So we have here the limit as h approaches 0 from the right. We take the limit as h approaches 0 of the right from both sides. We have here limit as h approaches 0 from the right. F of c plus h minus f of c over h is less than or equal to the limit as h approaches 0 from the right of 0 equals 0. So we see that the limit as h approaches 0 exists and equals the limit as h approaches 0 from the right. So we have here the derivative of fc equals the limit as h approaches 0 of f of c plus h minus f of c over h equals the limit of as h approaches 0 from the right of f of c plus h minus f of c over h. So the derivative of f of c is less than or equal to 0. So if we divide inequality 2, jumping back to up to number 2 point here in this proof, we divide that by h, and h is less than 1. So essentially we say that h now is negative. So we divide that by h when h is less than 1, and so the inequality symbol is reversed. And so we essentially repeat the process with the inequality symbol turned around. So we have f of c plus h minus f of c over h is greater than or equal to 0. Then we take the limit as h approaches 0 from the left instead of the right this time. So we have the limit as h approaches 0 of f of c plus h minus f of c over h equals the limit as h approaches 0 from the left of f of c plus h minus f of c over h is greater than or equal to 0. Therefore, the derivative of f of c is both less than and greater than or equal to 0, meaning that it must be equal to 0.
So now
So I'm going to pause just for a second there. That proof is a nice proof, and it's a little bit challenging, but the basic idea is that we're showing that if f is differentiable, then at places where you have a min or a max, the derivative must be 0. And intuitively, it's easy to see if you think about the picture, right? So if I have a smooth function that rolls over a max here, then I have to have a horizontal tangent line there. That's what Fermat's theorem is saying. And the proof, because we have to work sort of directly with the definition of the derivative, is a little bit hard to follow. But Fermat's theorem just says if f is smooth and has a min or max at x equals a, then f primed of a must be 0. That's what Fermat says. The converse to Fermat's theorem is false. Just because f primed of A is 0 does not mean you have a min or a max there. But you can kind of see in this picture, right? If I'm going to have a max, that means a local max. That means this has to be the highest point anywhere nearby. So that means you have to go from increasing on the left to decreasing on the right, which means your derivative has to go from positive on the left to negative on the right. And the only way for the derivative to go from negative to positive is for the derivative to, at the point in between there, be equal to 0. So the horizontal tangent line here is equivalent to saying that f primed here is 0. And similarly, the horizontal tangent line here is equivalent to saying that f primed of B here is 0. So the idea is to go through a max, you have to go from increasing to decreasing, which means f primed has to go from being positive to negative. So by the intermediate value theorem, as long as f primed is continuous, the derivative has to go through 0, meaning that you have to have a horizontal tangent line. So the kind of takeaway from Fermat's theorem is that one of the ways we can find mins and maxes is by finding places where the derivative is equal to 0. And it's important to illustrate that the converse is false. Note, just because f primed of A is equal to 0 does not mean we must have a min or max at x equals A. And the thing you can think about here is like the cubing function, right? X cubed. If we look at the cubing function, he looks like this. This has f primed of x equal to 3x squared. So f primed of 0 is equal to 0. But there is no min or max at x equals 0. So sort of the idea of Fermat is if you have a local max, then you must go from increasing to decreasing. Or if you have a local min, you have to go from decreasing to increasing. If you go from increasing to decreasing, you must have a horizontal tangent line. And if you go from decreasing to increasing, you must have a horizontal tangent line. But there are other ways to have horizontal tangent lines where you don't go from increasing to decreasing, like this. This guy is increasing and then increasing, but he happens to have a horizontal tangent line right here. So Fermat's theorem says if you have a min or a max, then f primed should be 0 at that point. But just because f primed is 0 at some point doesn't necessarily mean you have a min or a max there. And this is a good example of that. So you have to be a little bit careful.
We're going to be talking about critical numbers, which is a number in the domain of a function f in which either f prime of c equals 0 or f prime of c does not exist.
All right. So that last sort of thing was the idea of a critical number. A critical number is anywhere in the domain of the original that the derivative is either 0 or undefined. So I'll go ahead and move to his third video now. Are there any questions for Kevin so far? Okay, yeah, and I'll go ahead and move to the third video.
Here we have our first example. So find the critical numbers of f of x equals x to the 3/5 power times 4 minus x. So the first thing we're going to want to do is we're going to want to use a product rule. So that's going to get us to x to the 3/5 power times -1 plus 4 minus x times 3/5 x to the negative 2/5 power. And that's going to get us out to negative x to the 3/5 power plus 3 times 4 minus x over 5x to the 2/5 power. And we bring the negative x to the 3/5 power into the fraction with common denominator addition. And so we get negative 5x plus 3 to the 4 minus x, 3 times 4 minus x, all over 5x to the 2/5 power. And so the final function that we get here at the end is 12 minus x all over 5x to the 2/5. And once we have the function, we find where the function is going to be either equal to 0 or undefined, meaning that it's going to have 0 in the numerator or in the denominator. So we take the numerator and we set it equal to 0. So we get 12 minus 8x equals 0. And when we solve that, we find that the numerator is equal to 0 at x equals 3 over 2. And then we take the denominator and we do the same thing. So we set it equal to 0, and we find that if we plug x in equal to 0, we can find that since 0 is multiplied by 5 and raised to the 2/5 power, we can find that where it's going to be undefined by plugging 0 in for x. And so 0 is going to cause the denominator to be undefined. And so 0 is a critical number.
I'm going to pause here for just a second and go back one little bit here. So everything Kevin said again is correct. And what he's showing you is more or less verifying that these numbers are critical numbers, that 3/2 is a critical number and 0 is a critical number. But I want to emphasize how we find these. So using the product rule, we get this as its derivative, and then we simplify to this form over here, 12 minus 8x over 5x to the 2/5. Once you've simplified your derivative, the trick is to set it equal to 0. If I want to know where my critical numbers are, I need to know where, or for what x values, is f prime either undefined or equal to 0. To find where f prime is equal to 0, I take this, which is the derivative, and I set the whole thing equal to 0, which is equivalent to setting the top to 0. So to find where f prime is equal to 0, we set 12 minus 8x equals 0. That's what he's doing down here. And then you can solve for x, and that will give you the 3/2. Similarly, if we want to find where f prime, this thing, is undefined, we set the bottom to 0, and that's what he's doing here. So the critical numbers we get by calculating f prime and then figuring out where f prime is 0 or undefined. F prime will be undefined if the bottom is 0, and f prime will be equal to 0 if the top is 0. That is a good general rule. The only thing we need to check then, once we have those two numbers, is that they're both in the domain of the original. Remember, in order to be a critical number, you need to make f prime 0 or undefined and be in the domain of the original function. Now, since this function here has a 5th root in it, but no other weirdness, his domain is actually all real numbers. So any number we found that made f prime 0 or undefined would be a critical number for this automatically. But it will happen sometimes that you find places where f prime is 0 that aren't in the domain of the original. Or you'll find places where f prime is undefined that aren't in the domain of the original. And you need to be mindful of that definition. In order to be a critical number, it must make f prime 0 or undefined and be in the domain of the original. And again, to find where f prime is 0, we'll usually set the top equal to 0. And to find where f prime is undefined, we'll usually set the bottom equal to 0.
And so 0 is a critical number. And we can also graph our answer. So we see that this graph supports the answers x equals 1.5, where f prime c equals 0, and x equals 0, where f prime c is undefined, as there is a horizontal tangent at x equals 1.5 and a vertical tangent at x equals 0. So here we have another example. Find the critical numbers of f of x equals y minus 1 over y squared minus 1 plus 1. So our first step here is we use the quotient rule. So we get y squared minus y plus 1 times 1 minus y minus 1 times 2y minus 1 all over y squared minus y plus 1 squared. And then we keep on simplifying that, and then we find where the function is equal either to 0 or is undefined. And for this one, I couldn't find any values of the denominator that would cause it to be undefined, but I did find 2 values of the numerator that could cause it to be 0, and thus cause the whole thing to be equal to 0. And those 2 values were 0 and 2. So 0 and 2 are both critical numbers.
A quick note here, if we wanted to, we could use the quadratic formula to find where the bottom is equal to 0, right? We can compute the discriminant really quickly to see if any of those exist. So b squared minus 4ac, b squared is 1, negative 1 squared, minus 4 times 1 is negative, is 1 minus 4, is negative 3. So the discriminant of the quadratic that appears inside the square downstairs is negative. So it's not just that Kevin couldn't find them, they don't exist. There are no real numbers that make the bottom 0 here. But in general, if we're having a hard time like factoring or finding them, the quadratic formula would help us here, would tell us what to do. But Kevin's correct that the only critical numbers here come from the top being 0, and we can get that by factoring. You factor a y, and this becomes y, or you can factor a negative y, that's fine. And you get negative y times y minus 2.
2. So 0 and 2 are both critical numbers. So here we are introduced to the closed interval method. To find the absolute maximum and minimum values of a continuous function f on a closed interval a comma b, we're going to want to first find the values of f in a comma b, and then we're going to find the values of f at the endpoints. The largest of these values is the absolute maximum, and the smallest is the absolute minimum.
There is one thing we need to inject here. So in your notes, item 1 here, we need to find the values of f at any critical numbers in a comma b. Of course, we can't write down the value of f at every number in the open interval a, b, because there's infinitely many of those. So make sure number 1, when you're writing this down in your notes, you write find the values of f at any critical numbers in a comma b. And this might have been a typo in the textbook or something like that. That's okay. So first we find the critical numbers, and then we find the values of f at those critical numbers. Then we find the values of f at the endpoints. The largest of all of those will be your absolute max, and the smallest of all of those will be your absolute min. This is kind of the method that goes along with the extreme value theorem. The extreme value theorem says any continuous function on a closed bounded interval must have an absolute max and must have an absolute min. This is how you locate that absolute max and absolute min. First, you find the critical numbers. Then you evaluate f at each of those critical numbers. Write down those y values. Then you evaluate f at the endpoints. Write down those numbers. The largest of all of those is your absolute max. The smallest of all of those is your absolute min.
In our first example here, we're going to want to find the absolute maximum and minimum of the function f of x equals x cubed minus 6 squared plus 5 on the closed interval -3 comma 5. So the first thing we're going to do is we're going to find the value of f at the critical numbers.
I think this is 6x squared.
Comma 5. So the first thing we do is we take the derivative of the function we see at the top, x cubed minus 6 squared plus 5, using the power rule, and we get 3x squared minus 12x, and we set that equal to 0. And so now we can factor out 3x, and we get 3x times x minus 4 equals 0. And we see at which 2 values of the x does that equal 0. And we get here that it equals 0 at 0,
yeah, that's okay.
X equals 0, and x equals 4. So we plug in the x values after that, and we get f of x equals 0 cubed plus 6 times 0 squared plus 5, and that's going to give us 5. And then we plug in 4, so we get f of x equals 4 cubed minus 4 times 4 squared plus 5, and that gets us to -27.
I think this should really be f of 0, and this should be f of 4, but this is the idea. So we found the critical numbers. The function is x cubed minus 6x squared plus 5, whose derivative is 3x squared minus 12x. We can factor that. So 0 and 4 are the critical numbers. And so this would be f of 0. F of 0 is equal to 0 cubed plus 6 times 0 squared plus 5, which is indeed 5. F of 4 is 4 cubed minus 6 times 4 squared plus 5, which is negative 27. So we're recording these y values. The first y value we write down, f of 0 equals 5. The second y value we write down, f of 4 equals negative 27. And then the last few things we do is evaluate at the end points. So f of negative 3.
And then we plug in the values at the end point, which is negative 3 comma 5 here. And then we get f of a equals negative 3 cubed minus 6 times negative 3 squared plus 5, and that gets us to negative 76. And then we're going to do the same thing with 5. So we get 5 cubed minus 5 squared plus 6 equals negative 20. So we look at the lowest and the highest numbers in total there, and the lowest number is negative 76, and the highest number is 5. So the absolute maximum is 5, and the absolute minimum is negative 76.
And we might want to, if we were sharing this, back a little bit, if we were sharing this with someone else, we would say the absolute maximum is 5, and it's attained when x is 0. And the absolute minimum is negative 76, and it is attained when x is negative 3. So these are the min and max values. But it's also nice to tell us where they happen. So the absolute max is 5, and it occurs at x equals 0. And the absolute min is negative 76, and it occurs at x equals negative 3. There's some little notation issues here, so I just want to make sure everybody's comfy. It's difficult to typeset mathematics, and even when we look at it, I did review this. I don't think I caught this or these little issues last time we reviewed this. So are there any questions on this example? Are we all comfy with what's going on here? Everybody gets the process? Take the derivative, set it equal to 0. If there was anywhere this derivative was undefined, we would have to find those two. Then we plug in all those critical numbers. That'll get us the y values on the graph of the original at the critical numbers. Then we plug in the endpoints. F of a, well, a is negative 3, so f of negative 3 is negative 3 cubed, blah, 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 which is negative 76. F of b, which is f of 5, is 5 cubed minus 6 times 5 squared plus 6, negative 20. So we take these y values, which are 5, negative 27, negative 76, and negative 20. The absolute max is the biggest, which is 5. The absolute min is the smallest, which is negative 76. Let's look at the next example.
So the absolute maximum is 5, and the absolute minimum is negative 76. So in this next example, we do pretty much the exact same thing. So find the absolute maximum and minimum of f of x equals x cubed minus 3x squared plus 1 on the closed interval negative 1/2 comma 4. So we're going to find the value of x at the critical numbers between negative 1/2 and 4. So the first thing that we do is we find the derivative of the function up top using the power rule. So we get f prime of x equals 3x squared minus 6x, and we set that equal to 0. We find that we can pull a 3x out of that, so we get 3x times x minus 2 equals 4. And we see for what values of x is the function equal to 0, and we get x equals 0 and x equals 2. So we plug in the x values, so f of x equals 0 cubed minus 3 times 0 squared plus 1 gets us to 1. And then we have f of x times 2 cubed minus 2 squared.
Yeah, this would be f of 0 and f of 2.
Plus 1 gets us to negative 3. And then we plug in the values of the endpoint, negative 1/2 comma 4. And plugging in negative 1/2, we get negative 1/2 squared, or cubed minus negative 1/2 squared plus 1 equals 1/8. And then we do the same thing for f of b. So
I think these x's should be plugged in, right? So these x's shouldn't be there. It should be just negative 1/2 squared, and this should be 4 squared.
Plus 1 equals 17.
So he's saying the
And
right things.
so
There's
we
just
look
little
for the
typos.
highest number and we look for the lowest number. We get an absolute maximum of 17 and an absolute minimum of -3. And that's about it for my student teaching lesson. So thank you guys so much for watching.
So nicely done, Kevin. This is essentially the whole game with mins and maxes. It's not terribly hard. If there's something that we're taking away from this, maybe it's that typesetting mathematics is a pain in the ass. But I think the lecture there was well delivered, and as long as we're able to get nice clean notes out of this, the typos shouldn't harm anything. So first, let's acknowledge Kevin's hard work here. This is well done, and it's not an easy thing to do. Typing math is genuinely a pain in the ass. I'll show you guys what I use to type mathematics if you want to see it here. This is something I started learning around the time I was in Calc 2, Calc 1, somewhere around there. It's called TechMaker, and it's a good tool. There's a bunch of other stuff like this. Here's it's really a bunch of code. It's kind of a pain in the ass, but you see, this is kind of what's necessary to get mathematics to render nicely. And I acknowledge that you guys working in the Microsoft products like PowerPoint and whatnot, Word, very, very hard to get good math to render correctly without any errors. So I don't hold anybody accountable for any little typographical issues. I would like to run through, just because we have the time, I think we're ending up with a meaningful amount of time left. I'd like to run through just one or two more examples and show us some pictures along with them so we can look at some of the stuff. While I'm queuing up the examples, are there any questions for Kevin or myself based on the lecture? Yeah, definitely nicely done. This stuff is a lot of fun. So we see here the textbook's definition of an absolute max and an absolute min. An absolute max is, you have an absolute max at x equals c if f of c is bigger than f of x for all x's in the domain. And we have an absolute min at x equals c if f of c is smaller than f of x for all x's in the domain. And then a local max and local min are defined similarly. We say that f of x has a local max if f of c is bigger than f of x for all x's nearby, and a local min if f of c is smaller than f of x for all x's nearby. And these are the same pictures that Kevin showed in his lecture. This is a good example, right, where we get the idea of local and absolute extrema being the same. And certainly it is possible for a point to be both a local and an absolute extremum. X cubed, this was the picture I drew earlier where you do have a horizontal tangent line at x equals 0. But even though you have a horizontal tangent line there, you don't attain a min or a max. Let's run through, let's see, was this one that we did? So continuous closed interval. I'd like to do something where we have some interesting stuff happening at a vertical tangent line or something like that, where we're really likely to get into trouble. So let's see what we have here. Something. Yeah, we'll go down to one of those. Before we get into this, I want to say some excellent problems for you guys to work on that I cannot assign in WebAssign because WebAssign is not very good at this, like telling you to sketch a graph. All of these, where they say, sketch a graph that's continuous on this interval and has the given properties. 7 through 10 in 4.1 are excellent problems for getting comfy with these concepts. 11 is very good. Sketch a function that has a local max at 2 and is differentiable at 2. Sketch a function that has a local max at 2 and is continuous but not differentiable at 2. Sketch a graph of a function that has a local max at 2 and is not continuous at 2. So I would like to work one of these, and I think maybe what's this other one? Absolute max, but no absolute. Local max. So 12, this is technically not possible. This is what I meant when I said the book has some issues. Any absolute max is automatically a local max. Sketch a function 1.2 that has an absolute max but no absolute min. Yeah, okay. So I'm going to work numbers 11 and 13 here for you, and I would like you guys to come in and work some of these on your own too. So 11 asked us to sketch a graph that has a local max at 2 and is differentiable at 2, local max at 2 and is continuous but not differentiable. So let's do this. This is 4.1, number 11. A sketch a graph that has a local max at x equals 2 and is differentiable at x equals 2. And then I'll sketch my graph there and have part B. Here we're going to sketch a graph that has a local max at x equals 2, is continuous at x equals 2, but is not differentiable. I'm going to abbreviate differentiable as diffable at x equals 2. And then one last guy, C, sketch a graph with a local max at x equals 2, but is not continuous at x equals 2. We're going to look at all three of these cases. So having a local max and being differentiable, that's the case we're mostly familiar with. It's like if here is 2, then anything, like this would do the job. Here I clearly have a local max there. This is the top of a hill. And because I am differentiable and have a local max, according to Fermat's theorem, there has to be a horizontal tangent, and that's what we see. If you're smooth and you have a local max, got to have that horizontal tangent. Well, this is sufficient. If I'm going to have a local max, I'm looking at part B now, at x equals 2, be continuous but not differentiable there, that means something kind of weird has to happen. I'm going to draw two pictures here. I could have something like this going on, sort of like an absolute value function, but flipped over, right, where this is a sharp corner. Or, and this is the sort of behavior that I'm excited to illustrate to you guys, there could be something there called a cusp. Or not only is there like a sharp corner, but things are like very pointy. So in both of these cases, I still have a local max at x equals 2. And we are continuous at x equals 2, right? The graph is a single unbroken piece. But we're not smooth. So here we are continuous, but not differentiable. And we still have a local max there. So what kind of critical numbers would I get here? Right, we said this is like a horizontal tangent line. So here, f primed of 2 would be equal to 0. What about here? What is f primed of 2? Here, this would fail to exist. And here, this would also fail to exist. Because of the sharp points, f primed is not defined. Here, on this guy, f primed of x would be going to infinity as x goes towards 2. And here, there wouldn't be anything special. F prime would just have a jump discontinuity at 2. And then kind of the last of these cases, If I'm going to have a local max at 2, but not be continuous there, certainly I can't be differentiable there. Sort of the easiest way to do this is something silly like this. Here, this definitely satisfies the definition of a local max. This is the tallest point on the graph nearby, right? But the graph is not continuous. So these are kind of three types of pictures, or 3 different sort of things you can associate with local extrema, local maxes in this case, but local mins, you can imagine flipping all these pictures over and you get local mins. So all of these things can happen. And all of these are consistent with Fermat's theorem. Here, since f is continuous and differentiable, we know that f primed has to be 0 there. Here, f is continuous, but it's not differentiable, so I can't say f prime should be 0. But in both of these cases, f primed is undefined, and that is, again, consistent with what we've seen, right? 2 would be a critical number there. 2 is also a critical number here. F primed is equal to 0 everywhere on the domain here, except at 2 where it's undefined. So all of these are consistent with the theorems, even though they're, these latter guys are not really what we normally picture. Normally we picture something like this. And I want you to be ready for things like these, not just in terms of the pictures, but also in terms of the algebra, which is why I'm including this little bit here, that at a cusp like this, that's a place where f primed is going to infinity or negative infinity. It could be either one. In this case, we're going to positive infinity over here and negative infinity over here. So these are the different kind of things that local maxes can look like. The other one, whoops, sorry. The other one like this that I wanted to look at, oh, it is here, okay, is 13. So a function that's continuous on -1, 2, but has an absolute max, but no absolute min. Is this possible, the thing they're asking for in 13a? What's weird about what they're asking for in 13a? So I'm going to sketch the graph of a function on -1, 2 that has an absolute max, but no absolute min. What's weird about this? So we all just watched Kevin's lecture, right? I have here a closed bounded interval, but I want a function that has an absolute max, but no absolute min. What does that appear to contradict?
It has to be an absolute minimum.
Yeah, right. We said a continuous function on a closed bounded interval has to have an absolute max and an absolute min. So if this is not going to have an absolute min, what must be true?
The function is probably not continuous.
Very good. Yeah, Jonathan and Julio both giving really good answers there. The theorem that we appear to contradict here is the extreme value theorem. And for precisely the reason that Julio said, well, if I had a continuous function on a closed bounded interval, then it must have both a min and a max, an absolute min and absolute max. But here they said they don't want it to have an absolute min. So in order to avoid contradicting the extreme value theorem, like Jonathan said, we have to be drawing a function that's not continuous. Okay, let's see if we can do this. Kind of the silliest example here is a line. Alrighty, here's my x-axis, here's my y-axis. I'm going to call this -1. I'm going to call this +2. I'm supposed to have an absolute max, but I'm not allowed to have an absolute min. So this better not be filled in. But my domain still has to be the closed interval from -1 to 2. So I can't just leave this open and call it a day. But what I can do is come in here and fill it in like this. So now this is a function whose domain is the closed interval from -1 to 2, but it's not continuous. Specifically, it's not continuous over here. All right, so this function has an absolute max right here. And if this were filled in, making the function continuous, it would also have an absolute min. But it doesn't have an absolute min because I broke this little piece off and moved it up here. So this is the kind of challenge. If you start removing things from the extreme value theorem, you can see what happens. And that's a really good thing for any student of analysis to do. See, if I start taking away hypotheses, what can you do to the theorem? Can I break the theorem by taking away the requirement that the function be continuous? And the answer here is yes, right? It is possible to have a function on a closed bounded interval that doesn't have an absolute min. The catch is the son of a bitch can't be continuous. There's lots of other ways to do this too. This is just sort of the simplest one. Part B had another request like that. Sketch a graph of a function on -1, 2 that is discontinuous, but has both an absolute min and an absolute max. Okay, well, I'll do the same thing here. I'll set myself up. I'll call this -1. I'll call this over here +2. I want to be discontinuous, but still have an absolute min and an absolute max. Well, there's lots and lots of ways to do this. Here's a dumb way to do it. I say dumb, meaning like not unwise, but like kind of silly. Here you go. There's your absolute min, and here you go. There's your absolute max. This is definitely discontinuous, right? This graph is not a single unbroken piece. I have a removable discontinuity here and a removable discontinuity here. But there's lots of other ways to do this too. Show you just one more way to satisfy the criterion in part B. I could do something like coming up with answers here that are piecewise linear is fun, but discontinuous still has absolute min and absolute max. I could do something like this. So there's your absolute max. Actually, let's do it like this. There's your absolute min. Okay. So here the absolute max is here. Maybe I'll mark this as 1/2. The absolute min is down here. This function is discontinuous, but it still has an absolute max and an absolute min. So there's lots of ways for this extreme value theorem to kind of be dissected. If you remove the continuity hypothesis, you can still have interesting things happening, right? Like here's a discontinuous function for which the extreme value theorem still holds. Still has or still appears to hold, right? Still has a local min or an absolute min and an absolute max, even though the function is not continuous. Here's another function that is discontinuous on the closed bounded interval -1, 2, but still has an absolute min and an absolute max. I think sort of the fun way these things can happen is how you can break the theorem by removing the continuity hypothesis. So here's a function that is defined on a closed bounded interval, but does not have an absolute min. And the only way to do that is to make the function discontinuous. There's lots and lots and lots of other examples, and I really would like you guys to come up with your own. So please make sure you come in here to 4.1, and in addition to the WebAssign problem, do some of these like number 7 through number 14, where you're sketching graphs that have the specific criterion, sketching them by hand. This is probably the most important thing you can do in this section, besides like just raw calculation of critical numbers and stuff. The other thing I wanted to show you was extreme values coming from vertical tangent lines. And I think number 39 would be a good example of that probably. Is there something a little simpler? Yeah, let me work a simpler example, and then I'll let you guys go. All right. Maybe not. We'll do the whole thing. How about it? How about it? Let's do it. Let's find the critical numbers. Can I find all absolute mins, absolute max? No, I'd like to find all the extrema, or something that is kind of interesting. They don't have anything that challenging. Okay. We'll do 39. Find all extrema for f of x equals x to the 4/5 times x minus 4 quantity squared. All right. So when we say find all the extrema, what we mean is find all the mins, all the maxes. And here's my function. It's worth noting the domain right away, because we want to be able to say whether something is or is not a critical number. Since this is a 5th root, if this was like a 4th root or a square root or an 8th root, my domain would just be the positive reals and non-negative reals, because you can't take an even root of a negative number. But the domain here, the domain of f, is all real numbers. So any number that makes f prime 0 or undefined is automatically a critical number. All right, find f prime and critical numbers. I used to use the hashtag symbol, which we back in the day called the pound sign, to represent the word numbers. We can't do that anymore because it means other things to you guys. So f primed, it's just me getting old. F primed is a product rule thing. I'll differentiate the first guy. That's 4/5 x to the 4/5 minus 1 is negative 1/5 times x minus 4 squared plus x to the 4/5 times the derivative of this piece, which is 2 times x minus 4 to the 1 times the derivative of the inside, which is 1. That's it. A little bit of chain rule over here inside a product rule overall. This looks a little bit scary, so I'm going to show you a trick for cleaning this up. F primed of x, I'm just going to copy it down over here, and I'm going to write the number. Oh, yeah, we'll write it out like this. So this is 4/5 x to the negative 1/5 times x minus 4 quantity squared plus 2x to the 4/5 times x minus 4. In order to find out where this is 0 and where this is undefined, I need to kind of figure out what's going on with this negative power. One way to do that is to try and write this all as one fraction, right? Rewrite this as 1 over x to the 1/5 and then have a common denominator between all the pieces. But there's a neat trick that works well here, and that's to force factor the largest negative exponent. So force factor the term with the largest negative exponent. In that case, that would be the x to the negative 1/5 term. He's the only guy with a negative exponent. So I'm going to force factor that out. I'll have then x to the negative 1/5 times 4/5 times x minus 4 squared plus 2 times. Now, if I force factor out x to the negative 1/5, that's the same as like dividing all these terms by x to the negative 1/5. So what's going to happen here? I'll have x to the 4/5 divided by x to the negative 1/5. This is going to become an x to the 4/5 plus 1/5, which is x to the 1 times here x minus 4. So this is a very neat algebra trick, and I want you to think about how that force factoring works. This trick can save you a lot of time on these sort of problems. Now, while I'm here, I might as well also force factor out the 4/5, or at least force factor out the 1/5. So let's see what that would look like. So if I bring out the 1/5, in addition to that, just kind of getting rid of all the nasty pieces, this will be 4 times x minus 4 quantity squared. When you divide out by 1/5, the 1/5 goes away. And this would become a 10. So I'll have 10x times x minus 4. The algebra steps here are a little bit tricky, so you're going to need to go back through this carefully and justify each of these steps. But notice that if you distribute the 1/5, this would become a 4/5, and this would become a 2. 10 times 1/5 is 2. 4 times 1/5 is 4/5. And similarly, if you come back a step and you redistribute this x to the negative 1/5, this would become 4/5 x to the negative 1/5 times x minus 4 squared. And this would be x to the 1 times x to the negative 1/5, which is indeed x to the positive 4/5. So the factoring here is legitimate, and you need to practice it. It's a tricky factoring thing. It's called force factoring. And you can Google about this. There's lots of YouTube videos out there, I'm sure. It's not something I teach my non-honors sections, but I think you guys as honor students should take a look at this, because in practice, it's something I do all the time. And it's something anytime somebody solves these sort of problems, you need to do them. It's also by far the fastest way to solve these problems. So this piece out front, I can rewrite as 1/5 times x to the 1/5. And then the piece inside here, I can start cleaning this shit up. So this is 4 times x squared minus 8x plus 16 plus 10 times x squared minus 4x. And that, if I distribute the 4 up here, I'll get 4x squared minus 32x plus 4 times 16, is that 64? And then plus 10x squared minus 40x. And all of this goes over 5 times x to the 1/5 power. Now we can combine our like terms. I have a 4x squared plus 10x squared. Right, 4x squared plus 10x squared, that's 14x squared. I have a minus 32x and a minus 40x. That's going to be minus 72x. And then what else do we have here? We have a plus 64. And then downstairs, I still have my 5x to the 1/5. I need to factor the top. in order to find where f primed is equal to 0. So I'm still just simplifying f primed. This is divisible by 2, this is divisible by 2, this is divisible by 2. I don't think there's anything larger I can pull out, so let me go ahead and just do that. That'll give me 2 times 7x squared minus 31x, is that right? No, 36x, yeah? 36x. And then plus 64 divided by 2 is 32 over 5 times x to the 1/5. All right. So then the question is, can we factor this? I'm sure the answer is yes, but it's going to take a little while here. So rather than running through that and burning up your time, I'm going to factor 7x squared minus 36x plus 32. See if it happens. Yeah, it does. 7x minus 8 times x minus 4. So this is 2 times 7x minus 8 times x minus 4 all over 5x to the 1/5. So it's a meaningful amount of work to simplify f primed here. But then what does this tell me about my critical numbers? Well, where is f primed of x equal to 0? That's anywhere the top is 0. So that's going to be 8/7 from this factor and 4 from this factor. And then from the bottom, f primed of x is undefined at x equals 0, right? X to the 1/5 is 0 if and only if x is 0. It's like saying the 5th root of x is 0. So these are my critical numbers, right? And that's what we were told to find. Now, there are some other theorems that I want to talk to you guys about for finding mins and maxes. Let me see really quick if they address any of those in here. I thought the first derivative test was going to show up in here, but it might not. Closed interval method. Yeah, no, this waits for graphs of f and f primed. How derivatives affect the shape of the graph. Yeah, okay, so we'll have our increasing, decreasing stuff and first derivative tests coming later. So I won't bombard you with that, but I do want to take these critical numbers. I'll put them in Desmos. So x equals 0, of course. Sorry, let's just do a fresh graph. X equals 0, x equals 8/7, and x equals 4. And then I'm going to throw in the graph of the original, which is f of x equals x raised to the power of 4/5 times x minus 4 quantity squared. So look at what we have here. I'll rescale my y-axis a little. Here we are. So at x equals 0, I have a min here. And it's a pointy one. It's a cusp. And that's coming from f prime being undefined. You guys see that? The original function here gets very pointy. And it kind of bounces like that with this min at x equals 0. And the fact that this is kind of pointy corresponds to the fact that f primed is undefined at 0. And then here I have a max. Did I type this wrong? 8/7 or 7/8? 8/7. 8/7. Ooh, it looks like maybe we missed something here. This should be at 1. I'm I'm suspicious of that. And then our other guy is over here at 4. So I don't know if this is a rounding error in Desmos or something else. Probably not. Probably there's an algebra mistake I made somewhere in here. But I just wanted to show you guys the difference between the cusps, where you have a pointy min like this, and these guys that are coming from where f primed is equal to 0. So these are kind of the nice Fermat's theorem case, and this is kind of the nasty one. All right, that's where I'm going to leave it for today. I'll hunt back through this and see if I can find the algebra error, although I'm not sure there is one. Did I mistype something here? X minus 4, x to the 4/5. Oh, I did. Yeah, this is 5, not a 6. There it is. Oh, sorry, I just typed it wrong. Yeah, here we go. So 0, and then at 8/7, and then at 4. So beautiful stuff, right? This is Fermat's theorem and everything Kevin just lectured on, kind of in one picture. We're going to learn how to tell whether something is a min or a max just based on the algebra of the derivative. I'll let you think about how that can happen, how you know this is a max rather than a min. There's sort of 2 ways to think about it. And same thing here, how to know if this is a max or a min without looking at the graph, right? Without using Desmos. But that's it. I hope you guys have a good rest of your afternoon. There's a new homework that's going to drop today. I saw an email from Kevin saying, or somebody, I think it was Kevin, saying that the exam wasn't graded yet. Everybody's test should be graded. Should have been graded by like last Wednesday. So if your test hasn't been graded for some reason, please do send me a message if you're unable to see the grade. All the grades should certainly be in by now. And if you have any other problems or questions, curiosities, anything like that, come by my office hours and I'll see you guys there or in our next class. And then I think on Friday, we may have one more student lecture, depending on whether I have time to get through everything here. Yeah, so if I see this message here, if yours hasn't been graded, definitely look at the comments, see if there's something going on there. I'll take a look. Maybe there was some sort of problem. But that is it. Take care, guys, and I will see you next time.